Now when you're working with very small objects, like molecules or atoms, it is very convenient to have a unit that is about the same size as what you're trying to work with. When we're trying to talk about the masses of atoms and molecules, it's nice to have a unit that we're not going to have to use scientific notation for. We want the unit to be about the same size as what we're measuring. That really is the rationale for everything that I am about to say. Now, we've been using atomic mass units in the last lesson to talk about what the mass of an atom or the mass of a molecule is. What is an atomic mass unit? One atomic mass unit is about approximately the mass of either one proton or one neutron. Both of those have a mass of about one atomic mass unit. Now, we saw also in the last lesson that that's off a little bit, that statement. It's not exactly 1 AMU for a proton, and not exactly 1 AMU for a neutron. They're a little bit different, and the neutron is just a tiny, tiny bit heavier than the proton is. Now, but that's roughly true. You know, to 2 or 3 significant digits, you're going to be fine saying that the weight of this is 1 atomic mass unit. The weight of that is 1 atomic mass unit. Now, this has some abbreviations. U is the officially defined abbreviation for atomic mass unit, and this is what you see in most technical papers now and most textbooks. Your textbook uses the older abbreviation, which you do occasionally see. It's AMU for atomic mass unit, but this is the better one. So you should try to always use that symbol for the atomic mass unit. That is the official SI abbreviation for atomic mass units. All right. Speaking of the SI, they came along and they redefined atomic mass units. It used to be that this was exactly 1 atomic mass unit, but they said let's redefine it so that it's easier experimentally to relate it experimentally to an object. It's hard to get like just 1 proton in isolation, but it's pretty easy to get a carbon atom in isolation and talk about its mass. So they redefined this, an atomic mass unit. This equal sign with an extra bar on it means defined as is that it is 1/12 the mass of a carbon-12 atom. Let's remind ourselves real quick about all the stuff that's in a carbon-12 atom. We talked about this in the last lesson. The 12 is the mass number, and that's the total number of protons and neutrons. And if you look at the periodic table, you will see that the atomic number for carbon is 6. So there are 6 protons. Let's draw them as little red circles. And there are 6 neutrons. Let's draw them as little open circles. So the nucleus of a carbon-12 atom looks something like this. How many electrons are there going to be? Well, you need an electron for every proton. Let's draw them like we were in the last lesson as little purple particles that are zipping around out here. These are the electrons. And there's got to be 6 of them if it's a neutral atom, okay, and not an ion. So That's what a carbon-12 atom, we can picture it as looking like that. If you take this pile of stuff, 6 protons, 6 neutrons, and 6 electrons, and you divide it by 12, that's an atomic mass unit. So the mass of this atom is exactly 12. According to the official definition. That's kind of the standard. That's how they define atomic mass units. Now maybe you can see why these aren't exactly integers anymore. Because we're dividing the mass of these by, the mass of all this stuff by 12. It's not going to be just a proton mass or a neutron mass. It's going to have that little extra bit from the mass of the electron coming in there. Okay, so you can do this, you can use atomic mass units to express the masses of atoms, and it is real easy for you to just look up the masses of atoms. If I want to look up the mass of a copper atom, on the periodic table, they give me the average mass of a copper atom. So there are several isotopes of copper atoms, but if you look at the average mass of all atoms of copper on Earth, it's 63.55 U. So it's pretty easy for you to get the masses of atoms in atomic mass units. What about molecules? Suppose I've got a water molecule. It's got a couple of hydrogen atoms stuck to an oxygen atom. How do I get the mass of one water molecule? Well, all I got to do is add up the masses of the atoms that are in there. There are 2 hydrogens, which, according to my table, have a mass of 1.01 U. And there is 1 oxygen, which, according to my table, has a mass of 16.00 U. And I can add those together, and I can get the mass of 1 water molecule. It's 18.02 U, right? Now, that's kind of useful in relating molecules to mass. I can relate the mass of a water molecule, 1 molecule of H2O, I can say, has a mass of 18.02 U. So 1 molecule of H2O is 18.02 U of H2O. Now sometimes I will take not just mass units, but also the name of the substance after it. And that's kind of a good habit for you to get into, because we're going to be doing problems that involve several different substances, and it's important to be clear on which substance you're talking about. So you include that in the units. Now let's do a little problem with this conversion factor. Let's suppose that we want to figure out how many atomic mass units I've got in a drop of rain. Well, let's figure out how many water molecules I've got in a drop of rain. So a drop of rain weighs about 0.05 grams. And what I'm trying to do is turn it into molecules of water. Alright, well, we just had a conversion factor. What I'm trying to do in the problem is link a mass to molecules. And we just had a fact that we could use that does link a mass to molecules. I know that 18.02 U is equal to 1 molecule of water. So I've got a link between a mass and molecules. This is the critical link here. So I don't have U anywhere here, so I'm going to have to drop U into my root map there. And this is the link then that I need there. Now I'm missing a link here. how many grams are there in a U, or how many U are there in a gram? And we get a kind of a strange number when we look at the conversion factor. You may instantly recognize this if you've had any high school chemistry at all. That number will kind of jump off the page at you. It is a famous number called Avogadro's constant, or Avogadro's number. And this is where it comes from. You may have wondered where that number comes from. It is the number of atomic mass units there are in a gram. So it comes from the way we have grams defined and atomic mass units defined. So this is the missing conversion factor that we need here. So to finish the problem, I have all of my conversion factors listed. I need to just turn them into fractions, right? What has to go down here? Okay, well, I want to get rid of grams of H2O. So grams of H2O has to go down there. And I'm using this link. 1 gram of H2O is 6.022 times 10 to the 23rd U. Okay. That gets rid of grams of H2O. But now I have U. I'm trying to get to molecules, so I have to use this link. Where does the U go? I need to get rid of this U. I need to get rid of the U to get to molecules. So I have got to cancel out that U. It has to go down here. And this is where the 18.02 is going to go, right next to that. So if you're confused about why I'm putting all this stuff where I'm putting it, think of it like this. You write down what you're starting with. A raindrop, 0.05 grams of water. You got to get rid of the grams of water, so on the bottom of the next fraction you have to have grams of water. And you need a relationship. You need the top and the bottom here to be equal. You need a link between grams and something else. And here we have a link between grams and atomic mass units. Now, then I've got atomic mass units, and I want to get rid of that, so the U have to go down here. And I have a link between U and molecules, which we just talked about how to get that. Now, this is going to give me a big number. I mean, I could do the math here. It'd be, let's do it, just so you can see how it's punched in. I've got 0.05 times, okay, and it's using scientific notation on my calculator right now, 6.022 EE 23 divided by 18.02. And it's 1.67 times 10 to the 21. And what are the units? Everything canceled except for molecules. So the units are molecules. And I don't have the right number of significant figures here, right? Raindrop, I'm not so sure what the weight is. It might be 0.06, it might be 0.04. So I only have one significant digit there, and I should only have one here. So if I'm going to report this to the correct number of significant digits, I'll round it off to one figure. And it'll round up to 2 here. And that will be my answer. That's about how many molecules there are in a raindrop. That's a lot. If I were to write that number in scientific notation out as a decimal number, it's kind of ridiculous. It's a 2 with 21 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That's a big number. That's a lot of molecules. So molecules are incredibly small. Alright, this thing I put a box around is kind of important. If someone asks you, where does Avogadro's number come from? You say, it comes from the definition of an atomic mass unit in terms of grams. That's where that number comes from. Now, we're going to use this number in the next frame to define a fifth SI unit for you to know, the mole.